to you today, and then I will switch it over to, I'll use an example that's not in the book to help explain it and make sense of it. So first of all, I want to know the probability of events A and B occurring. All right. I take the probability of event A, and then I multiply it by the probability of event B, given that I know A has already happened. So let me give you an example. I have 7 red marbles, 5 blue marbles. And I want to know what the probability of picking 2 red marbles out is. So I want to pick 2 red marbles out. I want to know what the probability of it is. So to begin with, I could do a tree diagram. All right, so I put red, I put blue, 7 out of 12, 5 out of 12 to start with, red, blue. Now what happens on the second one? I've already picked 1 marble out, right? In this case, I picked a red one out. So what's the probability to get a red on the second one? 6 out of 11. This would still be 5 out of 11. And red, blue down here would be, that means I picked a blue, so that's 6 out of 11. And then this would be 4 out of 11 here. Okay, so that's what a tree diagram, that's all of my outcomes possible there, right?
7 on blue.
7 here. Thank you. Good. Okay. All right, so I want the probability that I get 2 reds. So a red and a red. So I find the probability of getting red on the first one. What's the probability of getting red on the first one? 7 out of 12. 7 out of 12. Now I want to know what the probability of getting red on the second one is, given that I already took the red one out in the first place. 6 out of 11. So I multiply it together. 42, and what is that? 132. That'd be 42 out of 132. If I'm doing it using my tree diagram, I just simply multiply those two together. But the point of this is this. This is what we call the condition. The condition is I find the probability of B given I already know what A is, on the condition that I know what A is. So in this case, I was solving for probability of A and B. But what happens if I want to solve for the probability of B given that I already know what A is? That's what we call conditional probability. So I go probability of B condition A. All right, probability that B given that I already know what A is. That's the probability of A and B over the probability of A. So all I simply do is divide that over to this side, which makes sense, right? Right now it's multiplying and divided over to that side. Okay, now that I put a condition on it, I have reduced my sample space when it comes to the question. Okay, now I can do these questions with more logic than I can actual mathematical formulas. Logic works in a better way here. So let me give you an example. I have a 6-sided die. My sample space for that 6-sided die is 1, 2, 3, 4, 5, and 6. That's the entire sample space. Now, I want to know what's the probability of getting a prime number given that I know it's an even number. So now I am reducing my amount of sample space, because if I look at what this is saying, I want to know what's the probability of prime given that I already know that I rolled an even none. So let's look at this. What did that reduce my sample space to by making sure that it was even? Half. What are the 3 outcomes?
2, 4, 6.
2, 4, and 6, right? So now I only have 3 possibilities, correct? And of those 3 possibilities, how many of them is prime?
1.
1. So what's the probability of rolling a prime number given that I know it's an even number? 1 out of 3. I can reduce the sample space because I'm on condition here. I've already made a conditional statement. I know that it was even, therefore it's 1 out of 3. So if I want to use my equation then to solve this, probability of A and B, so that's the probability of prime and even. All right? So how many of those numbers are prime and even?
1.
1 out of 6 possibilities, correct? Over the prime, then it's an even number. Well, how many of those are even numbers out of the 6? 3 out of 6. When I divide fractions, multiply by the reciprocal. Based on condition, the probability of getting a prime number, given that I know it's even, is 1 out of 3. So when you're talking about condition, that is reducing the sample space you are working with. Does everybody understand what I'm saying there? Okay. I can use the formula, but common sense, a little bit of thinking actually gets it done a lot faster without using the actual equation here, because I now know that I've reduced my sample space from my 6. Okay? All right. Now, let's look at a conditional question. Page 138. We're going to go through question 4. Jason remembers to set the oven timer 70% of the time he bakes banana bread. So, timer, no timer. So the probability that he sets the timer is 0.7. What's the probability he doesn't set the timer?
0.3.
0.3. When he does remember to set the timer, the probability that he will burn banana bread is 0.15. Burns it, doesn't burn it. 0.15, 0.85. Okay, so far? If he doesn't set the timer, the probability that he burns it is 0.75. Doesn't burn it, 0.25. So those are all my possible outcomes now. Those are all the possible outcomes. So what's the probability that he set the timer and burnt the bread? 0.7 times 0.15. What's the probability that he did not set the timer and then did not burn the bread? 0.3 times 0.25. Those are all of the possible outcomes. But this one has placed a condition on it. What is the probability that Jason burnt the banana bread today? So what's the probability that he remembered to set the timer? So we know that he burnt the bread. So now that eliminates 2 possibilities. That eliminates this guy and eliminates that guy. Because we know he burnt the bread. Now I need to know what is the probability that he set the timer. So by doing this, what is it? Probability that he set the timer, given that he burnt the bread, is the probability that he set the timer and burnt the bread over the probability that he burnt the bread.
Don't you have to switch those? Because it's B given A is equal to A and B over A.
Yeah.
I think it's got to be divided by T, or else you got to flip your first one.
Well,
Yesterday he did it like that, and it gave us the right answer.
yeah. It doesn't matter if I go TUB or BUT.
Okay.
Doesn't matter.
Okay.
It's just, it's and. It implies both, right? It implies this.
Okay.
Okay? I understand what you're saying. The biggest thing, Austin, and this goes for everybody, because this is, I sometimes forget this, is that letter right there and this one down here have to be the same. That's the most important part. How you put T and B or B and T, doesn't matter, but the letter that's on the given, the conditional, has to be there. Okay, so now, how do I find TUB? How do I find the probability that he set the timer and burnt the bread?
Times.
I times those two branches, that's right. So 0.7 times 0.15. Right? So that's probability they set the timer and burnt the bread. Now, I need to know what's the probability that he burnt the bread. Well, 0.7 times 0.15 and 0.3 times 0.75. Okay, now most importantly, for this question to work, you are going to always have an addition on the bottom here. Remember that. You will have an addition on the bottom. All right, because if you don't have the addition on the bottom and you put it on the top, it's going to cancel out and you're going to end up with a pretty skewed value. So you 0.7 times 0.15, and you're going to have to remember that this on the bottom, if you're going to solve it all at once, needs a bracket on the bottom for all of that. Okay? Any questions so far? Punch that out. What do we get?
0.33.
31.
1/3?
Yeah.
Is it 1/3? Right on the money?
3182.
No. 31.8%.
Oh yeah, I just divided it out.
0.318?
Yep.
Okay. This concept will seem confusing to you, but it's very straightforward when you consider you have to eliminate some of the outcomes in order for you to solve for that. All right. Any questions? Okay. Number 6 was a bit of a tricky question yesterday. 7 caused a bit of grief too. So when you're working through it, expect to hit a little speed bump there on 6 and 7. Okay. That's it. I think those that are close to done are done can do 5, 6 without any instruction. It's on independent events, which just means that you don't have, that would be like replacing the marble. So on the example I did, you'd be replacing the marble. So then it doesn't matter what you do in the first, it has no bearing on what happens in the second. Or if you're rolling a die and flipping a coin, it's actually more like it. Okay. All right. Finish 5-5 for tomorrow, please. Or Thursday, I guess. Please and thank you. Okay. And I don't know if I did much more than that